Hello, CEP 637. So today we're going to talk about assignment 5, which is multiple linear regression, but we're also going to include some other components that help us to refine our argument about whether or not something is practically significant, and then also understanding whether our model is actually appropriate. And so first let's look at the directions in the assignment. So you'll note that there's some additional variables being added to our model. In particular, the language variable, which asks students if their language that they spoke at home was the same or different as that of the test. We are adding students' opportunity to learn, specifically where students were asked about their experience with applied math tasks. And we're going to dichotomize that. And then confidence toward solving an equation. So if we go to the code book, you can see that here. ST25Q01 is the language variable. And so over in SPSS, I will just go ahead and type that in here as language. And if we go back to the code book, we can see 1 means same, 2 means different. So I'm going to add that here. And then we have the opportunity to learn. ST76Q01. So if we go back to SPSS, I'm going to put that in here. And then 1 means frequently. 2 means sometimes. And 3 means rarely. And we will need to dichotomize this. So what we're going to do is say at least sometimes. So 2 and 1 will recode later as a 1, and then 3 will become a 0. And then the last one is confidence, which is ST37Q05. And it goes from very confident to not at all confident. So in SPSS, I will put confidence, and specifically, this is confidence in solving a simple two-step equation. I will actually put that in there as well. And SPSS, it looks like, is thinking. All right, now I'm back. I had to close SPSS to reopen it. All right, so Q05, 37Q05 is going to be confidence, and specifically towards specific types of equations. And this is going to be a 1 means very confident. A 2 means confident. 3 is not very confident. And 4 is not at all confident. And I misspelled that there. All right, so we're going to also be dichotomizing this one into 2 categories, confident and not confident. So 1 and 2 will become a 1, and 3 and 4 will become a 0. And the same thing with the previous one that had to do with opportunity to learn. Remember, that one had 3 categories, so we will code this one to mean at least sometimes they had the opportunity to learn. And this will help us better understand the classroom context and whether that had an impact on their math scores. All right, going back to the description here, the instructions. So we're going to have this specific order: ESCS, language, female, enjoy, math career, opportunity learn, and confidence. But first, we need to dichotomize. So let's create, I've already dichotomized gender and math science career. I have not dichotomized enjoy math. I'm going to still leave that like that. So opportunity to learn. Go to transform, recode into different variables. Grab the opportunity to learn variable. And I'm going to call it OTL2. Old and new values. So this one, remember, had 3 options. So we're going to tell it that if it's a 1, which meant frequently, it's going to stay as a 1. And if it's a 2, it's also going to become a 1 because 2 meant sometimes. So we want both a 1 and a 2 to be translated into a 1 so that this will mean at least sometimes. And then if it's a 3, we want it to be a 0. Click continue, click OK. And we see that it came up here at the bottom, OTL2. It is listed as nominal. We want that to be a scale. And we can put over here in the values, I'm going to put 1 means at least sometimes, and a 0 means rarely. Okay. And then we need to create a new one for confidence. So first reset this so it pulls everything back out. Confidence, I'm going to call this confidence 2. Change old and new values. Don't forget to put the system missing in there. So with confidence, if it's a 1 or a 2, we want it to become a 1 so that 1 and 2 means that they are at least somewhat confident, and a 3 and a 4 meant that they weren't. So 3 and a 4 are going to become 0. Don't forget to click the add button so you can check it here to make sure these are correct. 1s and 2s become a 1, 3s and 4s become a 0. Continue. Okay. And we see here we need to add this label. A 1 means confident. A 0 means not confident. And we need to change it to scale. And now we're ready to run a multiple regression model. So we go to linear. PV1 math is the dependent variable. And now we need to make sure that we put everything in the correct order. I know SES goes first. If we look back, we can see that next should be language. I'm just going to leave that up while I change these. Oh, we forgot to change language actually. Let's go do that really quick. The language variable is ST25Q01. I forgot to fix this when SPSS crashed earlier. So 1 means same, and 0 means different, and 2 means different. Oops. So in this one, we'll make 1 be a 1 and 2 be a 0. So transform, recode into different variable, reset. Language. Click change. Whoops. System missing becomes system missing. What's going on? All right, let's try it again. All right, let's just reset it and try it again. For some reason, it's not liking me at the moment. I'm going to try 4 letters. Maybe it didn't like the length of the name. Old and new values. System missing stays missing. A value of 1 becomes a 1. A value of 2 is a 0. So in this way, 1 means the language was the same as the test. 0 means different than test. Click continue. Click OK. We see that it showed up at the bottom. I'm going to go ahead and put the labels in here. 1 means same as test. 0 means different than test. And then we need to change it to scale. All right. Now let's try this again. Regression, linear. PV1 math goes in the dependent box. Then we have ESCS. And then we need to put language. Remember, we're picking the new ones that we just created. So I'm looking at the very bottom of the list here. Language. And SPSS does not like me again. What is going on? Let me try this. Okay. So we put SES in here. We put language in here. And then we put female. Enjoy. Which, remember, we're going to leave it as a 4-point scale, but if you dichotomized it, that's okay. Math career, opportunity to learn, and confidence. Okay. Then we're going to make sure that we select all of these options: confidence interval descriptives, part and partial correlations, and collinearity diagnostics. So, first of all, we need to look at this. We want to verify that this is still okay to do with a linear regression. Under options, or sorry, not options, statistics, we're going to select confidence intervals, descriptives, part and partial, and collinearity diagnostics. Click OK. And let's see what it gives us. All right, we could look at a quick look at the correlation table here. Make sure that PV1 math is highly correlated, or at least has a decent correlation with everything. ESCS is pretty high. Language, gender, enjoyment, math career, opportunity to learn, those things don't look like they're that important. Confidence does look like it is an important variable. And then let's just look down at the other ones. So make sure that they're not highly correlated with each other. See if there's any issues with multicollinearity. So ESCS, looks like there's no high correlations there. Language looks good. Enjoyment has a somewhat of a correlation with math career and confidence, but not too bad. Those are still pretty small. Math career looks pretty small, and opportunity to learn is small with confidence. So overall, it looks pretty good. Nothing sticks out as problematic. Notice how R has gone up. That will always happen when you add more variables. So you have to be cautious. It doesn't necessarily mean the model is better. R squared is a bit higher. 28% of the variance in math scores is explained by this model that we created, statistically significant model. And let's go to the coefficients table. So on the right side, we see these collinearity statistics, tolerance, and VIF. If there is extreme multicollinearity, we're looking for a tolerance less than or equal to 0.1 or a VIF greater than or equal to 10. None of these things stick out like that, which tells us that the variables that we've included aren't causing any problems. They seem to each have their own unique contribution, or not any conflated contribution to the model. And then if we look at the statistically significant column, everything came back statistically significant except math career, which perhaps that is expected because math career, if we look back at the correlation table, has a correlation of 0.003 with math scores. So basically it's not related to math scores. So that's interesting. Once we put all this other stuff in, math career came out to not be that important. Or I guess it doesn't matter whether someone is in math, wanting to pursue math or science, I should say. Then we have these other ones. The effect sizes are pretty small still, with the exception of confidence. That one is really large, effect of 45. That's bigger than the socioeconomic status, but the other ones are relatively small. Confidence intervals are tight. If you look at the lower and upper bound for a lot of these, the tightest ones are for confidence and ESCS, the ones with the biggest effects. If you look at other ones, they dip down pretty low, anywhere from 6 to 11, 5.5 to 13.5 for language, 4 to 10 for opportunity to learn. So the effect sizes are, looks like the effect is not very big. And then we have this part column, which we can use to understand the unique variance that each is explaining within the overall variability of math. And remember, they are each taking up a specific proportion of this 28.7% that the model overall explains. So if we want to know what that looks like, we could say, well, how much does confidence actually matter? And these are our correlation values, so we have to turn them into little r squareds. So if we take 0.174 and square it, it explains about 3% of the variability, whereas the ESCS variable, which has a part correlation of 0.452, that one explains quite a lot more. That one explains a little over 20%. So even though confidence effect size is larger, confidence is only explaining about 3% of the this total 28.7%, and about 20% of this 28.7 is being explained by socioeconomic status, which only leaves about 8.7% left to explain. So, and then the rest, of course, is explained by these really, really small amounts over here. So, this coefficient cannot be used to determine the effect size like you would think. Yes, it has a bigger impact, but it explains a smaller amount of the variability. All right, and then we could look at the residual statistics. Once again, it looks appropriate. And so we are good on that end. So if we go back to the description here, do you think there's an adequate correlation between each IV and the DV? Some of them are really small, so you would want to point those out. Nothing looks problematic, though. Do you think there's any issues? Yes. Sorry, no. There's not any potential issue between independent variables. And you will later explain that again in the collinearity statistics section. Examine the first regression output, interpret R squared, F. Okay. What do the tolerance and VIF columns tell you? Well, they've told us that there's nothing to be concerned about. The part correlation, we have just discussed that. And then we could write out the linear regression equation, which is going to be PV1 math equals intercept plus ESCS plus language and so forth. And then we would put the coefficient estimates as prefixes to each one of these variables in the model. Using the equation in number 6, what is the average expected score for a female who enjoys math, whose language is different from the test, who does not want to pursue a math career, had at least some experience with applied math task, is not confident, and 1 standard deviation below the mean in ESCS. So, if they're female, that means the female variable gets a 1. If they enjoy math, then that means they also get a 1. 1 means strongly agree. Language is different from the test, that would get a 0. Who does not want to pursue a math career, well, I guess we should word that as who wants to pursue a science career, so we'd put a 0 in there. Had at least some experience with applied math tasks, so that's the opportunity to learn variable, that would get a 1. And who is not confident, so confidence would get a 0. And 1 standard deviation below the mean in ESCS, so we'd have to think globally. 1 standard deviation below the mean would be a -1. So we would put that in, compute what that is, and that would give you the average expected score for that type of person. And then you could compare that to someone whose language is the same as the test. And I'll leave you to answer that for now. We will talk about that in class. All right, so one thing we didn't do is this part number 3. So let's get to that. Part number 3 says to run the same regression model, except this time choose stepwise. All right. So we're going to go over here. Analyze regression, linear. And you'll see here it says method. I'm going to choose stepwise. Click OK, and let's look at this output. So, variables entered and removed. That's new. You can see the first variable that was entered was ESCS. Nothing was removed because it was the only thing in the model. Then confidence 2 was added. Nothing removed. Enjoy math was added. Nothing removed. Female was added. Language was added. Opportunity to learn was added. And then that's where it stops. But there was another variable in there called math career. So math career was not included in any of these models. And if we look down here, you can see in this list of predictors here, you can see the first model, ESCS. So there's the R, 0.494. R squared is 0.244. Then confidence was added, and then enjoy math was added, and then female was added to the model, and then language was added to the model, and opportunity to learn was added to the model. And so what this is telling us is that math career, for some reason, didn't have enough of a statistically significant improvement to any of these models, and therefore was not added to any of them. And if you remember, it was not statistically significant in the model that we just ran previously. You can see the ANOVA table, and there are on the side all 6 models, which it tells you what they include underneath the table. So all 6 models are statistically significant. And then we get a coefficients table. It looks large because it's giving you output for each model. So we can see what the coefficients look like. We can see the part correlations and how those change as things get added to the model. And we can see also how the effects, the impact of each of these variables changes as these variables get entered. The excluded variables table tells you which variables that you listed are not included in each model. And you'll notice that math career is the only thing listed in every single one. So in the last model that includes all the other variables, math career is listed here because it did not make the cut. And what this process is doing is it is adding a variable one step at a time. That's why it's called stepwise. So it starts with the first variable, and it's trying to find which variable by itself explains the most variability. And then it goes on to the next one. So what we didn't do when we ran this a minute ago is include in the output the change in r squared. So if we go in here and go to statistics, r squared change, this will help us understand whether or not adding a variable caused a statistically significant improvement over the previous model. So you can see here on the right, we have these change statistics, r squared change. So adding confidence added an r squared change of 0.036. And actually, if we go down here, 0.036 should be associated with the square of 0.19. Telling us how much it was added because that's the unique contribution. So, where'd it go? Here it is. And you can see on the right side, it does an actual test to see, grabs a p-value, and every single variable that got added related to a statistically significant improvement in the model. But look how small some of these improvements were. So this one was an improvement of 0.36%, but the other ones were very small, 0.3%, 0.2%, 0.1%. So remember, even though those are statistically significant improvements in the model, they may not be practically significant improvements in the model. So we might be willing to stop at model 2 and just say that these other models don't matter. So in other words, enjoy math, gender, language, and opportunity to learn are all variables that don't contribute enough to the model to include them. Or maybe you want to include them for theoretical reasons because people think they should matter, and that way you can talk about them and their lack of statistical significance, even though they're believed to have practical significance. All right, and then everything else pumps out the same exact thing that we've already looked at. So that is this assignment. Let's check and make sure we've answered all of the questions. And I will leave you to answer these on your own to think about why some of these things might need to be included or not. All right, that's it.